Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will do a couple of examples about finding a confidence interval for the parameter mu under the assumption that we are dealing with normal data and the variance is known. Okay? So, as I said already, we're assuming that we have a simple random sample of size n coming from a normal distribution, mean unknown, variance known, right? And we know that the formula of a confidence interval for the parameter mu, in this case, is given by a point estimate plus minus a margin of error. So the point estimate for the mean mu will be the sample mean x bar plus minus c star. This guy represents a number coming from a normal 0, 1, c star. Sometimes you're going to hear the term critical value. So c star is a critical value, meaning just a number coming from a normal 0, 1. And sigma divided by the square root of n is the standard deviation of our estimator, x bar, right? We know that the variance of x bar is sigma squared divided by n. Therefore, its standard deviation will be sigma divided by the square root of n. Make sense? And this guy, the critical value, c star, depends on the confidence level that you want. Okay? The higher the confidence level, the larger c star will be. Okay? Well, now let's see that problem, the first problem that we're going to be doing together here. So we have a magazine, right? And these guys are estimated. These guys are interested in estimating the household income of its readers. Okay? Okay. So we have a sample of size 80, right? So n, the sample size is 80. Based on past experience, they assume that sigma is 30,000, and from that sample that they have, they came up with a sample mean of 119,155. Okay? Okay. So now what we would like to do is develop confidence intervals for that estimate, okay, of the mean of the average annual household income. Okay, we're going to do a couple of these, and then you can do the other one, okay, as a kind of a homework problem to practice. So let's do parts A and B together. So let me call this guy example 1, if you will, because we're going to be doing another one. So we have our formula, right? X bar plus minus c star times sigma divided by the square root of n, right? So formula x bar plus minus, let me see, we have it here, plus minus c star times sigma divided by the square root of n. Okay, So for part A, what we want is a 90% confidence interval, right? 90% confidence interval for mu. And mu represents the mean, the average annual household income. Okay, that's our parameter of interest. So let's go back to what we have here to get the information that we need. So the sample size is 80. So sample size 80. What we have is that also that sigma is 30,000. And we have a sample mean $119,000 155. So 119,155. Okay. So now let me introduce something that maybe you'll see in other textbooks, right? So alpha. So remember that what we want is a 90% confidence interval. So the confidence level is going to be given by 1 minus alpha, and it's going to be 0.9, which implies that alpha is 0.1, okay? So, and sometimes you're going to see the following notation for that formula, okay? Using that alpha notation, what we want is this guy here, right? What we want this guy here is to be a number such that the area to its left or to its right is alpha divided by 2. Okay? Make sense? Because we know that C star, the notation that we used before, is a number such that between negative C star and C star, right, we have a desired confidence level, right? So if the probability that you want is C, then that would be C percent confidence level interval. That means that between negative C star and C star you have C, right? So in this case, what we have is, if you want to have confidence level 1 minus alpha, that means that what you need here is alpha divided by 2 and alpha divided by 2. Make sense? Okay, so let's keep going. Just notation, okay? So if you take a look at what we have, we already have x bar, we already have sigma, we already have n, so the only thing that we need is this guy, the critical value. If we have the critical value, we are done. We're going to be able to find the lower confidence limit and the upper confidence limit of our confidence interval, right? Okay, so let's find C star, or C of alpha divided by 2. Okay, so for a 90% confidence interval, so let's launch R Studio. We don't care about this. No, don't save it. So as we said, so alpha is going to be, in this case, 0.10, so alpha divided by 2 is going to be 0.05, right? So alpha equals 0.10. Then what we want is a quantile from a normal 0, 1, which is, you know, the default means 0, standard deviation 1. The probability that we want is alpha divided by 2, right? So negative 1.644, right? So it gives you the negative version of that guy. Make sense? So this is negative C of alpha, right? Let's double check and let's use our table, right? So our table is going to give us areas to the right, okay? So since we want a 90% confidence interval, right, we want a number C star such that between negative C star and C star we have between those guys 90%, and then that means that in the right tail we have 5% and 5% in the left tail, right? So it turns out that if you're using a table, the best that you can do is 1.64 or 1.65, right? Makes sense? So using R, we have something more accurate. Oops, not what I want. RStudio. This is the one, right? Negative 1.64. Make sense? Okay. So if you were to round this to 4 decimal places, there you are. Okay, so negative 1.645 basically would work. Okay, okay. So now we have everything that we need, right? So using R, this guy, our critical value is roughly negative, well, if we want the positive 1, we just change it to positive, right? 1.6449, right? And then we're basically ready. So the lower confidence limit would be x bar, which is this guy, minus this, our critical value, times sigma, which is 30,000, divided by the square root of our sample size. But our sample size is just 80, right? Make sense? Okay. So we might as well find it using R. Let me see. So it would be just 119,155 minus 1.6449 times 30,000 divided by the square root of 80. Okay, so $113,637.80 basically, right? So our lower confidence limit would be that. Note that the upper confidence limit, the only difference is going to be a sign, right? So upper confidence limit, have a plus instead. Let's make that change here as well. Okay, so upper confidence limit is well, $124,672.20, right? Okay, so that's it, right? So that would be part A of our problem, right? Let me go back to the statement of our problem. That would be our 90% confidence interval, right? So let's think about it. Let's see what is going to change if we want to do part B. If we want to do part B, right, everything is the same. We haven't changed anything. The only thing that is changing is the confidence level, 95%, right? So the only thing that is going to change is the critical value, C star, right? So let me just copy paste what we have, and we're going to make a few changes. So we have almost the same, but now 95%. That's the confidence that we want. If that's the case, then 1 minus alpha, that's a confidence level now, is 0.95, which implies that alpha is just 5%. And then when we want to find that critical value, well, that's going to be bigger. And by the empirical rule, we know that if you want two numbers that capture roughly 95% of your observations for a normal 0, 1, those numbers are going to be -2 and 2. Roughly, that's an approximation. The empirical rule is an approximation. But now we have an idea of what we're going to be getting. So let's change that alpha. Now let's find that critical value. So -1.9599 and so on, right? If we round this to 4 decimal places, -1.96, right? And we can check with our table that now what we want is, if between -C star and C star we want 95%, that means that in the right tail you will have only 2.5%. So 1.96, 0.025 exactly. So in this case, yeah, we were lucky. If you want a 95%, then you'll be able to find it exactly using our table. But we have R, so no problem. Anyway, it matches. So now we just change our calculations accordingly, right? So first, this guy is going to be 1.96. Then we are going to have 1.96 here, 1.96 here, and this is going to change, right? Okay, so let's see. So we have 1.96 here. Let's change that to a plus. That's it. Lower confidence limit, upper confidence limit, and we are done. So from this first example, what I want you to remember is that if you think about it, the hard part is finding that critical value that depends on the confidence level that you want, right? But if you have R, it isn't that hard. You just use that command qnorm that gives you quantiles of normal. Okay, make sense? Okay, so that's our first example. Now let me go back to our lecture notes, and you can do part C later, right? Now you know that the only thing that is going to change from what we already did together is the critical value. So now you want 99%. As you can expect, that critical value, C of alpha divided by 2, or C star, is going to be bigger, right? Because you want to capture more probability between negative C star and C star, okay? Okay. So now, and the solution will be there, okay? So just give it a shot, try it on your own, and then check your work, okay? So let's do one more. Let's do another example. This one, same conditions, right? We're assuming that we're dealing with a normal distribution, that our observations come from a normal distribution, that the variance or the standard deviation is known, right? And well, we want and that the mean is unknown, and that we want a confidence interval for the mean, okay? So the difference between what we had on the previous example and this one is that in this case I'm giving you raw data, I'm giving you observations, I'm not giving you summary statistics like before. So the only additional layer is, well, now you have to find that point estimate on your own, but it isn't that hard. We know that the sample mean, x bar, is just the sum of your observations divided by the sample size, okay? So you could check what we're about to do, but I would like to play around with R a bit more. So remember that we said this from the beginning when we started discussing this introduction to confidence intervals, that the assumption that the population variance sigma squared, or the population standard deviation sigma is known, is kind of unrealistic. So it turns out that due to that, R doesn't have a built-in function in it to find this sort of confidence intervals, but it's a great opportunity to learn how to define, how to create your own functions. So what I'm doing here is we're going to be creating our own function that computes confidence intervals under those conditions that we have been discussing. We are sampling from a normal, and the variance is known, okay? So the name of our function will be simple.z.test. It's going to be a function, right? And with this equals, we are assigning this function to this guy, simple.zTest. The arguments, the input that we're going to need are these: x, sigma, the confidence level, and since we're setting this confidence level equal to 0.95, that's going to be the default for our function. So first we compute the number of observations that we have, n, the length of that vector x that we have as an input. Then we compute the mean, the sample mean. Then alpha is going to help us find that confidence level that we want. Okay, so if you have if you want a 95% confidence, right, you know that alpha is going to be the complement, which is 5%, just like we just did, right? And to find that critical value, that C star, you need a quantile, but at this level, 1 minus alpha divided by 2. If you found alpha divided by 2, just like we did before, you would be getting, you know, the negative version. If you do 1 minus alpha divided by 2, you get the positive version of that C star, of that quantile. Okay? Now we know that the standard error, the standard deviation of x bar, is sigma divided by the square root of n, and then it's just the, you know, our formula, x bar plus minus C star times the standard error. Okay, so let's copy paste this. Now remember that, and this happened in another video where we wanted to copy a function, right, that for some reason when we copy and paste, those curly brackets change from an from curly brackets to an F and to a G. So that's why I opened a script and I pasted here, I edited here, and now I'm going to be copying and pasting onto the R console. Okay, now let's see if that works. This is our data set, right? So I'm using the built-in function C to to assign that vector to the object cars. And then what we do is we use our function simple.z.test. There you are. So it worked. Same thing. Okay? Okay. And finally, just the interpretation. And again, I want you to be careful with that confidence level, right? So yeah, we estimate that, these guys are going to be selling between 61 and 76 cars, roughly, right? And that 95% is telling us that if we were to do this 100 times, 95% of the time, we would be able to capture the true average, the true mean. Right? Make sense? Okay. So just to summarize, what we did here is just a couple of examples. We applied that formula for a confidence interval when we have data coming from a normal and we assume that the variance is known. The formula is just x bar plus minus C star times sigma divided by the square root of n. So the application is kind of simple. The tricky part could be just finding the critical values, those C stars, but it's not that hard if you have R, and if you're careful using a table is not that hard either. Okay? Well, that's it for now. Thank you so much. Take care. And, well, keep working hard. See you next time. Bye.